Submitting a new manuscript to a prestigious peer-reviewed journal places crushing pressure on graduate students and researchers. Every credible scientific communication relies on a strict, non-negotiable architecture, the IMRAD framework: introduction, methods, results, and discussion. To manage the heavy writing workload, many researchers feed their raw experimental drafts into standard, off-the-shelf AI models to speed up the process. They simply expect a polished, submission-ready manuscript. Instead, they receive a draft where the precise scientific context has been stripped away, leaving the research sounding amateurish. Relying on a generic large language model in this way is not a shortcut. It creates a structural vulnerability that jeopardizes your academic credibility before the peer review process even begins. To understand why the text degrades so quickly, we have to look at a computational failure called contextual collapse. The abstract of a paper requires fluid narrative synthesis to summarize broad findings effectively. A methodology section requires the opposite: rigid, reproducible, and mathematically exact procedural terminology. This split-screen diagram illustrates how generic models fail here. Large language models are blind to these structural boundaries. On the left is proper methodology text. On the right, the AI treats the input as uniform conversational text, triggering a cascade of errors. Look at the exact point of failure. The generic AI replaces highly specific domain verbs like centrifuged and titrated with conversational synonyms like spun around or mixed. This sudden drop in academic vocabulary signals a mathematical mismatch, resulting in an immediate Turnitin flag for AI-generated text. A standard large language model approaches your lab results like a creative writing prompt, removing the exact contextual precision required for scientific accuracy. The underlying issue lies in the mathematical architecture of off-the-shelf AI. This funnel shows the problem. Generic AI processes all text through a single probabilistic channel. Whether you input an intro, methods, or results section, the algorithm weighs word choices uniformly, producing a flat, homogenized output. This uniform processing strips away the intellectual framing and narrative flow needed to justify a research question in an introduction. Simultaneously, it relaxes the rigid constraint matrices required to document step-by-step reproducibility in a methodology section. The researcher is left with a dual failure. The output lacks the intellectual nuance to engage human peer reviewers, and its mechanical predictability makes it an easy target for detection software. Any algorithm that does not actively recognize which specific IMRAD section it is editing is mathematically likely to produce an academic mismatch. Turnitin catches this generic output by analyzing two specific metrics. Perplexity is the measurement of how predictable word choices are within a given sentence. Burstiness measures the variation in sentence length and structural complexity throughout an entire paragraph. Because generic AI relies on uniform probability, it produces low perplexity and low burstiness, creating a mathematically flat, predictable text signature. Human academic writing is dynamic. As a researcher shifts from the narrative of an introduction to the strict procedures of a methodology, their writing generates a varied and spiky mathematical signature. Turnitin's detection algorithms scan specifically for the flat mathematical signature left behind by standard AI models. Bypassing these detectors requires a system engineered to mimic the mathematical complexity of human academic tone, a calculation standard models cannot execute. Solving this problem requires a specialized architectural approach. This is the role of ThesisHuman.com. The primary differentiator is its specialized IMRAD Copilot capability. This flowchart illustrates the mechanism. ThesisHuman routes input data based on its structural role. When an abstract is processed, it routes down a dedicated pathway optimized for narrative flow. Conversely, a methodology section diverts down a separate pathway built strictly for procedural rigor. By treating IMRAD sections as distinct operational tasks, ThesisHuman preserves the structural boundaries that standard AI overwrites. The final output of this architecture is highly specialized humanization. ThesisHuman adjusts sentence structure and vocabulary to naturally increase the burstiness and perplexity metrics that human-authored text exhibits. Crucially, while it humanizes the surrounding prose, it places a structural lock on all scientific variables and jargon, ensuring your data points remain unaltered. By combining fluid structural humanization with locked empirical data, The manuscript aligns with the high-variance signatures that scanners identify as human work. This allows for humanized delivery while preservation of the exact scientific meaning and tone remains constant. In this test, when the original complex text runs through ThesisHuman, the output remains scientifically precise and returns a clean 0% AI-generated score. Navigating academic publishing requires technical precision at every stage of drafting. Successfully passing peer review means using software built upon the syntactic architecture of science. If you want a tool that actually understands the IMRAD structure and won't ruin your methodology, you need ThesisHuman.com. We left the link right down in the description.